Hi, everybody. Let's see you again. And let's start our lecture. Okay. Today, we have lecture number 18. And now we will be continuing the topic called estimation from measurement. And let's start from example. Consider the capacity circuit shown in this figure. And first, the capacitor is charged to voltage V0 using a constant DC voltage source. Switch is in position 1. Then it is discharged through the known resistance R, switch in position 2, and voltage decay during discharge is measured at known time instrument. The reciprocate tests are carried out, and you can see here on the table. The measured data are given, namely here. If the resistance is accurately known to be 1000 ohms, estimate the capacitance C in microfarad and the source voltage V0 in volts. To solve this problem, we assume the well-known expression for the free decay of voltage across a capacitor, as you may see from equation 1 on the top of this slide. Vt proportionals V0 times exponent from minus T over Rc. Take the natural logarithm for this equation, and we get equation for logarithm V and get us minus T over Rc plus logarithm natural from V0 with Y equal logarithm V, as you can see next row, and X equals T. Second equation represent a straight line with slope, as you may see from this equation, M slope minus 1 over Rc. And y-axis intersect according to this equation. Using all the data, the overall sample means and two useful summations can be computed, as you can see from this equation. Now, substitute these values in equation, we get equation for M and A as the next here. From this equation, we can find at the bottom equation V0 equals 20.61 volts. It should be noted, in this problem, the estimation error would be larger if we did not use logarithm scale for the linear field. So, after describing M, we can know as R equals 1000, we have the C equal 1 over 10.13 times 1000 farad, and get us 98.72 microfarad. Okay, nice. So we can obtain detailed results for this example by using the linear least square error curve fitting in MATLAB. In particular, we may use the M file, as you may see here. MATLAB results. Let's look at this slide, please. The obtained linear least square error is shown on the left part of this slide. As noted in the beginning of the present main section, least square curve fitting is not limited to linear or straight line, right? The method can be extended to a polynomial fit of any order. For example, In quadratic feet, the data are fitted to a second order or quadratic polynomial. In that case, there are three unknown parameters, which would be determined by minimizing their SSE, where the yes. Okay. All right. In the least square error method of estimation, or LSE, we minimize the average squared error between the data and the estimate. Even though LSE, or least squared error, is an optimization method, it is not necessarily the best method of estimation, because its simplicity assumes that the model itself is very accurate, similar to the chicken and egg controversy. Okay? Or it cannot separately account for model error and measurement error. For example, if the actual behavior of the data is nonlinear, but fitted model is linear, then LSE cannot properly compensate for that. And furthermore, if the data had a systematic error at an offset, the LSE method cannot remove cannot remove that. Another popular approach of parameter estimation is the maximum likelihood method. In the method of MLE, we maximize the likelihood of the estimated value, given the set of data that we have. In other words, we estimate the proper parameter value for the random process so that it would most likely generate the data set that we have. Interpretation, the MLE method is typically expressed as a recursive algorithm. A characteristic of recursive estimation is that it improves the estimation as more and more data values are supplied. MLE can estimate more than one parameter, like a vector or parameter simultaneously. MLE method estimates a particular probability distribution for the data, and it is the parameters of that probability function that are estimated by the method. If the probability distribution is assumed to be normal, like Gaussian, then the results for the two methods, LSE and MLE, are equivalent, and they generate virtually the same result. This also implies that if the probability distribution of the data is known and is not Gaussian, then MLE is better than LSE. Apart from parameter estimation, the MLE method is commonly used in hypothesis testing as well. The objective in that context is to select the most likely hypothesis by maximizing the likelihood ratio for the available data. And furthermore, since the MLE method is based on a probability distribution for the data, it can generate a confidence interval for the data. Suppose that a process and a sensor with some randomness, possibly in both process and sensor, produce the following set of actual or numerical data in a random manner. So y will be equal y1, 2, 3, and yn. Also, suppose that the random process or actual process and sensing that generated the data is represented by a probability distribution function with the following parameters: m equal m1, m2, mn, up to m sub r. These are model parameters and are unknown. The goal of MLE is to estimate the model parameter value of vector. So model parameter value of vector m with that most likely has produced the given set Y. But note that the same data set Y is already generated and known, but the model parameter M is unknown. The conditional probability density function, PDF, of data Y conditioned upon the model parameters M and denoted by F from Y over F. Since Y is known and M is unknown, F from Y, when F is a function of F. Yes? Okay. In MLE, we estimate by maximizing for F from Y over F. Specifically, as you may see, this first equation for M hat, and hence the likelihood functions L from M over Y, which is maximized in order to estimate the unknown M given by data Y, is defined, as you may see, in equation for A. Yeah, it should be the case. The role of M and Y are reversed in L and F, even though the actual analytical functions of L and F are identical, as indicated by this equation. But notably, L represents the likelihood of a particular model parameter Y, given a specific set of data generated by the process that is represented by that model, while F represents the probability of achieving the specific data through a probability model having the particular parameter value. Okay. Now, let's come to the next example. Example number 2. In the process of product quality monitoring, 10 items are randomly chosen from a batch of products and are individually and carefully tested. During testing, each product is either accepted or rejected, and suppose that such a procedure produces the data set Y, and we can see this Y, A, R, and 5I. Estimate the most likely probability P hat that a randomly selected product from the bunch of acceptable A. Okay, so let's start our solution. Let P be the probability that a selected product from the batch is acceptable. The probability of realizing the data set, as we can see, probability A, R, and so on, when P, and this we can get this expression. After transformation, we can get the final simple expression P in power 8 times in brackets 1 minus P over square. PR here, it stands for probability of. Okay? Now, and this equation, this first big equation, they're also a likelihood function. We need to determine the value of P that maximizes our likelihood function. The likelihood function L from M when Y. To obtain it, we may differentiate the second equation, equate to 0, and solve for P. Analytically, easier way to achieve the same result is to use the fact that the logarithm is a monotonically increasing function, and hence use simply logarithm from L as a modified likelihood function and maximize it. So we have logarithm L from P over that expression get us 8 logarithm P plus 2 logarithm in parentheses 1 minus 5P, right? differentiate, and we can get this last expression here. Whereas we may find that p hat equals O dot A. For the sake of completeness, we have to show that the second derivative of the likelihood function with respect to the estimated parameter p is negative, so that the likelihood function is a maximum, but not a minimum. In the present example, the first derivative of the logarithm likelihood function is 8 over p minus 2 over 1 minus p. And its derivative is minus 8 over p squared minus 2 over 1 minus p squared, which confirms that the turning point corresponds to a maximum, not a minimum. Okay? If the data are second and have the normal or Gaussian distribution, the MLE results take a particularly convenient and familiar form. Consider a random data set as a y1, y2, up to yn, and suppose that the random variables y sub I are second with normal distribution from mu and sigma squared. Another have, say, we have normal distribution here with mean mu and variance sigma squared. The PDF of y sub I is this equation, 1 over square root from 2 pi over sigma times exponent in this big expression. The joint PDF of the entire random data set, given the model parameters mu and sigma, get us this equation. Since y sub I is the second differential, the joint PDF is the product of the individual PDF. This is indeed the likelihood function of the problem. Due to the exponential nature of this function, it is convenient to use its logarithm version, as you may see at this third equation here. Yes, where is that? P is a product from 1 up to n. And all of the rest you already know. Okay? Differentiate via the mu and sigma separately and set to 0 to minimize the likelihood function, as in the last expression we can see here. And hence, we get the maximum likelihood estimate, as you may see at this second equation on the slide. Clearly, our first equation is identical to the least square estimate, which is known to be an unbiased estimate for the mean. However, the unbiased estimate for variance is the sample variance, where the denominator, as we can see, n minus 1, not as n here. Okay? Right. Let's see another example, number 3. In this example, we will use MATLAB to determine the maximum likelihood estimate for the Gaussian probability density parameters corresponding to the data of example, as presented at the slide here. And you have here this data. The MATLAB function MLE from X, as you can see here, generates the maximum likelihood estimates of the mean and the STD over normal or Gaussian distribution. We have solution at this slide. These values agree with the results obtained in exam. In particular, the MLE of the mean is the sample mean 4.997. The MLE of the STD is 4.0205. And hence, MLE of the variance is this value in power 2. And this value is almost 9/10 over sample variance, 4.6778 times 10 in power 4 minus 4, which was obtained in previous example. We have seen that in essence, MLE is an optimization problem. However, except for some special cases, the MLE optimization does not produce a convenient closed form solution. A numerical solution of the recursive form is desirable in such situation. This recursive formulation may be expressed in the following general form, as you may see at the first equation here on the top, where m hat represents the parameter that is estimated. In general, the recursive increment u, as you can see in the final part of this equation, depends on such factors as the data of m, which are measurements, the model error variance, the measurement error variance, and even the present estimated value itself. We start with an initial guess m dot with hat for the parameter. Then we update it in the increasing direction of the likelihood function L. Typically, it is more convenient to use logarithm L rather than L. Step by step, until the required update is negligible. And clearly, the required direction of update is a gradient or slope for delta of L with respect to m. Specifically, we need equation for m sub I hat, where k sub I minus 1 is the step weighting factor of the update in the I iteration. The gradient is given by this equation for delta. The weighting factor k also depends on such factor as the data or measurement of m, the model error variance, the measurement error variance, and even the present estimated value itself. It needs to be adjusted in each step for these reasons, and also because when the change in the gradient is smaller, then larger updates can be accommodated during iteration. Specifically, k should be inversely proportional to the second derivative of L per m. This second derivative is called the Hessian. This second derivative is negative because the gradient of first derivative decreases as we reach a maximum power point. And hence, the recursive formulation of the MLE may be expressed as equation for mi hat, as we can see here. After transformation in this, we can go to the final value. We continue the iteration until the new estimate is equal to the old estimate. This is specified tolerance. Suppose that we are given measurements of y of quantity m. So y of quantity m, which is estimated. The data y has both model error sigma L, also denoted by sigma y, which correspond to the error in the model that is used to represent m and or unknown disturbances that affect the true value of m, and measurement error sigma with the sub w. Sigma m and sigma w are also given. We need to determine and estimate m hat of m. And assumptions: first, Gaussian distribution, and second, zero mean model error, and zero mean measurement error. Since the probability distributions are Gaussian, we know that MLE estimate is the mean value given by the PDF F, and estimation error is represented by the as given by the PDF. To derive a recursive formula of MLE, we start with the bias formula, as you may see, as this slide as the first equation. Correspond to the prior value of estimated, correspond to the posteriori value of the estimate. And we should note it then in a recursive formulation, F from M corresponds to the previous estimate, and F when M corresponds to the new estimate once new data are applied. Normal or Gaussian PDF, as you may see on the second equation here, from A from B, and once M is given, and the randomness in Y comes only from Z of the measurement error W. And hence, the variance from Y when M equals simply variance from W. Also, once M is given, the mean value of Y is M. So both model error and measurement error are zero mean. And hence we have third equation for F from Y when M here. 1 over 2 pi square root times sigma W times E in power minus Y over M squared over 2 sigma W squared. Equation 4 and 5 can be used to determine the estimate M hat and the estimation error variance sigma MI squared. Recursively, as you may see as this second equation, and it will be seen a bit later that this result from the basis for the static Kalman field. And now next topic, today's lecture, scalar static Kalman field. Kalman field is a popular method of estimation using measured data. Even though it can be used to estimate parameters, as done with the method of LSE and MLE, it is more commonly used for estimating variables in a dynamic system. For example, if the variables sum or all that are needed to determine the dynamic state of a system are not available for measurement, a Kalman filter can estimate them in an optimal manner using measurement of output variables. This estimation is possible in the presence of both model error and measurement error. Model error usually random, and measurement error usually random too. This ability to remove or compensate for random effects, it means noise and disturbance, is the reason why it is called the filter, even though it is an estimator or an observer, right? Unlike the method of LSE, and in some cases with MLE, Kalman filter is able to explicitly and separately accommodate model error and measurement that error. This is an advantage when statistics of these two types of error are separately available. As we will see, Kalman filter uses a predictor corrector method where a model of the plot is used to first predict the estimated quantity and its error covariance, and then correct these two quantities by using the actual measured data. The predictor step generates a priori estimate and the corrector step generates the posteriori estimate. Discrete time Kalman filter uses a two-step recursive scheme to accomplish this. Okay? Now, we present a Kalman filter style recursive formulation for a scalar or static system. Estimation can be interpreted in general as estimating an unknown quantity m, a scalar or vector, using data y measured from the actual process in which the quantity m is embedded. Symbolically, we determine m when y, which is denotes m given y. Since m is unknown and y can be affected by various random causes, m itself is a random quantity. Hence, once the probability distribution of m is obtained, it completely determines m. In fact, it is the mean value or expected value of m that is determined with respect to some criteria, including optimization criteria. If m is not random, then the mean value alone is what is needed. If it is indeed random, other statistics will be needed as well to characterize its randomness. If the probability distribution of m is Gaussian or normal, then the two parameters mean and variance alone will completely characterize m. The mean value will give the estimated value, and the variance will represent the estimation error. This is the basis for the present approach. Specifically, we will present an algorithm to determine the PDF f for m when 5. The present formulation is for a static system. And furthermore, the process or model is the estimated quantity itself. In other words, the system model does not have any dynamics, and also it corresponds to the identity or no change operation of multiplying by 1. This means that the predictor step of the Kalman filter, which uses the model, is not needed. And only the corrector step, which uses the measured data to correct the estimate, is needed. Even though the process model is 1 in the error-free case, some model error may be present and hence is explicitly accounted for in the present algorithm. In deriving the present recursive algorithm, we make the following assumption. First, when there is no measurement error, the measured or estimated parameter p and the measurement data or data y is linearly related through a known constant gain c, which is called the measurement gain. We will encounter this again in the multivariable dynamic formulation of a Kalman filter, which is addressed in a later section of this lecture. The model error and measurement error are independent and Gaussian or normal random variable. Third, the model error where has a zero mean and sigma m. And fourth, the measurement error w has a zero mean and sigma w. If the mean value of the measurement error is in 0, it cannot be estimated by the present process of estimation. The measurement system should be recalibrated to remove the constant offset error in the region. Also, we assume that the mean value of the model error is 0. If the mean value of the model error is non-zero and known a priori, we can simply adjust the estimated value using the mean value, or so-called constant offset. What is estimated is the mean value of parameter. if the mean value of an error is non-zero and unknown, the estimation process cannot determine it, and this can be further confirmed by using the maximum likelihood method with the following choice of likelihood function, which is consistent with the Kalman filter approach. Specifically, as the inverse of the likelihood function, we choose, as you may see at this equation on the top, 1 over L equals E when M minus M hat squared times when the Y, in case Y. To minimize our values RHS of first equation, we require next expression here. Next, the top. The maximum likelihood estimate itself is a known quantity. Once it is estimated using the given data, and can be taken out from the expectation for mean operate E of the RIHS term. And hence the maximum likelihood estimate, as we can see the next equation here. M hat proportional E from A when Y. In other words, what is estimated is the mean value of M given the data Y. In the present problem, the objective is to estimate M using measurements Y. The measurement equation is equation for Y, next one here, Cm plus W. C here is the measurement gain, and as noted earlier. The variables and parameters in this equation are defined in the list of assumptions given in the beginning. Since W is non-mean, is zero mean, we have the following relation between the mean values of M and Y. As you may see with these equations from here, mu Y is simply C times mu M. Furthermore, since M and W are independent random variables, we have the from equation variation from Y, its variation from Cm plus variation from W, or C squared constant, we became the first one, variation from M plus variation W. And sigma square Y will be the same, constant C squared times sigma N squared plus sigma squared from W. In deriving the algorithm of the scalar static Kalman filter, we now restate the bias formula using F as the first equation here. According to one of our assumptions, all the PDFs in this equation are Gaussian. As recognized earlier, F from M corresponds to the a priori value of the estimate, and F when M when Y corresponds to the a posteriori value of the estimate. In a recursive formulation, F from M, as we can see here, corresponds to the previous estimate F from when M over Y corresponds to the new estimate, to the previous estimate, and new estimate once new data are applied. We have the following normal Gaussian PDF, as you may see equation here from F from Y to the next. Once M is given, the randomness in Y comes only from word of W. And hence, the variation when from Y when M is the same as variation with W. Also, once M is given, the mean value y is Cm. So we can get this Cm expression. W is 0 mean. And hence we have this equation as the point. Substitute these three PDFs equations as you may see in this first equation. And now manipulate the exponent term in final expression of the following next use expression. And will be very, very simple. M minus in bracket M mu M plus A and all in square. Well, follow this expression as you may see, and we have from this first expression. And after that, we can rewrite our second equation according to this variable. It follows from the last equation that the mean value of M given y is at this equation we have here. As discussed earlier, according to Bayes' formula, mu sub M is the a priori mean of M. And mu from this M when y is the new estimate of M. And similarly, in a recursive scheme, sigma sub M is the prior estimate of the STD of the estimation error. And also note that the estimated value of M is the mean value. Okay? It follows that the recursive formulation of the present estimation or static Kalman filter scheme isn't as this nice equation. After a bit transformation, it can get very simple form 1 over S times K sub I. Here the K sub I, the iteration process starts with the initial value. When we have initial value, sigma with M0 hat, which should be known. And this is the expected value of M before any measurements are known. Typically, this is then taken as the nominal or ideal value of the estimated quantity. And the iteration process starts with the initial value sigma M naught equals sigma M, which is the STD of the model error as it is. And here we have initial choice, that the initial choice should be valid for estimation error because no measurements have been made at I equals 0. It is seen that I sub I is simply the scaling factor between the measurement and the measured quantity, in our case 1 over C, weighted by K sub I. The form of this weighting factor and the overall recursive scheme may be intuitively justified, as indicated now. For this, consider the two extreme cases. For first, model error is negligible. In other say, sigma M equals 0, in comparison to the measurement error represented by sigma from W. And second, measurement error is negligible, so sigma W equals 0, in comparison to the model error represented by sigma M. Okay? So let's see example number 4. A structural monitoring system uses a semiconductor strain gauge to measure the strain at some critical location of a structure. The system consists of strain gauge, pre-circuit electronics, which convert the change in resistance of the strain gauge into the voltage proportional, and a data acquisition and processing system, which records the voltage signal and digitally processes it as required. In this example, the strain that is measured by the strain gauge represent the process. The strain gauge, bridge circuit, and recording of its output voltage represent the measurement system. The following information is known. Calibration constant of the monitoring system is equal 400 milli epsilon over 4 volt. We should be noting that 1 milli epsilon is 1 microstrain, or 1 times 10 in power minus 6 strains. Sigma m, it's 5 microstrain. Sigma w, 2 millivolt. Our measurements here were represented by this data. So we have a static, not dynamic model with the error-free part of model when equal 1. So it's described this here. So we have, in first case, the iteration when m hat equal 800, my epsilon, this seems as a reasonable nominal value for the strain in view of the gain data and the calibration constant. So the following MATLAB program is used to get the recursive static Kalman filter result, as you may see in this one. And according to this result, we may use 823.1408 as the estimated strain. But should note that the STD of the estimate has improved, and so error has decreased as the iteration process. Okay? And now, case 2. Next, let us change the starting value of the estimated parameter to 0, instead of more logical value of 800 m sub 8. That's it. In this case, we get the following MATLAB result, as you may see here. It is seen that the final estimate is almost the same. Exactly, we have 821.098 with the same level of estimation error. Let's see case 3. Now, let us increase the level of measurement error to sigma w equal 50 millivolts. This is equivalent to 20 m sub 1, mu sub 1, with the same starting value 0 for m hat. And we get the following MATLAB result, as you may see in this slide now. The final estimate now is 316.62 m sub x, which is clearly inaccurate and unacceptable. The reason is as follows. In this case, the measurement error is much greater than the model error, and hence the estimation has placed less importance on the new measurements. Even though we started with a very pure guess, 0, for the estimated value, the estimation did not improve rapidly for this reason. The estimated error STD of the estimation was also high. It's 3.92 compared to 0.2527 before, due to this reason. Had we proceed further with more steps of iteration, the estimate would improve. The results from these 3 cases are plotted in figure A. In particular, it is seen from figure B that the STD of the estimation gradually converges to a steady value. Yes, and you can see this example. That's it. Next, we use the conventional Gaussian MLE procedure, where we estimate the parameters, mean and STD, of the Gaussian distribution that would most likely generate the given measurement data y. And we get the following MATLAB result. This estimate is almost the same as what we obtained first with the static Kalman estimation. Also note that the STD obtained from this procedure get us 19.66. It's quite large because it relied entirely on the measurement and did not differentiate between model error and measurement error. And finally, we directly compute the mean and STD of the given measurement data using MATLAB. We have this in slide. When scaled back to the microstrain, the mean value is 823.2. This is in fact the least square estimate and is also the estimate obtained from the standard MLE with Gaussian distribution. The STD of the estimate is 0.0518 volts or 20.72 m sub epsilon, which is also comparable to what was obtained from the standard Gaussian MLE. The LSE method does not have the ability to indicate where the much of the error comes from, the model or the measurement process. In general, when only a few data values are available, the Kalman filter style recursive MLE is more desirable than the LS, as we have seen from the earliest result in this example, since the LSC is simply the average value of the data. And furthermore, as expected, the LSE estimate is identical to the value obtained using the conventional MLE with Gaussian distribution. In previous sections, we presented a static Kalman filter, where the process model was the estimated quantity itself. Since the model was an identity or no change operation, in that case, model equal 1 in the scalar situation. The predictor stage of the Kalman filter, which depends on the process model, was not needed. Only the corrector stage was needed. Now, we present the Kalman filter scheme for a linear multivariable dynamic system. This requires both the predictor stage, which uses the process model, and the corrector stage, which uses the measured data. Kalman filter is an optimal estimator. It performs estimation by minimizing the error covariance of the estimate. A dynamic Kalman filter is able to estimate unknown variables of a dynamic system using the following information. First, a linear model of the dynamic system, including statics or covariance matrix V of the random disturbances that enter the system, including random model F. Second, a linear relationship between the measurable output variables of the dynamic system and the variables to be estimated. And this relationship may be represented by an output formation matrix, also called measurement gain matrix. This matrix is usually called as matrix C, and also includes a random noise with covariance matrix W. And third, output measure. As noted earlier, a general Kalman filter uses a predictor-corrector approach, which consists of the following two steps. First, predict the unknown variables and the associated error covariance matrix. This is a priori estimation. This predictor step uses the process model and the covariance matrix of the input disturbances, including model error. And second, correct the predicted variables and the associated error covariance matrix. This is a posteriori estimate. This corrector step uses the measured data or output measurement, output relationship, and the covariance matrix of the measurement noise. Next, we present some preliminaries which need to be understood before proceeding to the algorithm of the dynamic Kalman filter. They concern the model of the dynamic system, response of the system, discrete time model, controllability, and observability, and the standard linear dynamic Kalman filter uses a linear dynamic model, which constant coefficients of the system that generate the variables to be estimated. The dynamic system has R inputs and M outputs. In particular, a linear time invariant state space model is used in this Kalman filter. Such a model may be expressed as a given in the following. State equation, usually it's coupled first order linear differential equation, is as may as you see in this first expression on the top. X dot proportional AX times BU. And output equation, coupled algebraic equation, and where the Y proportional CX plus BU. Where X, it may be X1, X2, and so on up to XN, transform. And nth order vector U is the nth order input vector. The same nth order input vector for Y. All these three vectors are defined as column vectors. Also, A is the system matrix. B is the input distribution gain matrix. C is the output measurement formation matrix. And D is the input of feed-forward matrix. It is assumed that the output Y is measurable. And also the model itself may have errors, which may be assumed additive, and hence represented as disturbance input. Often the matrix D is zero. It is non-zero only when the system has the feed-forward character. An illustrative example will be given a bit later. The rigid output shaft here in this example of a diesel engine prime mover is running as a known angular velocity omega from T, omega capital. It is connected through a friction clutch to a flexible shaft, which is turned drives a hydraulic pump. A linear model for this system is schematically shown in a picture B on the bottom. The clutch is represented by a viscous rotary damper of damping constant P1. And the stiffness of the flexible shaft is K units in torque per rotation. The pump is represented by a field of moment of inertia J, and we can see here on the right. And it's fluid load by a viscous damper of a damping constant P2. We can write two-state equation for this second order system, relating the state variables T and omega to the input omega capital, where T capital is the torque in the flexible shaft, and omega, and the next is the pump speed. We will consider two cases of the system output. First, omega 1, as we can see, is the angular speed at the left and the shaft. And B output omega is the pump speed. The state equations are derived now. The constitutive or physical relation for the shaft K, so that K capital, as you may see in the first equation. The constitutive relation for damper B is represented by second equation for T. Substitution equation 2 into 1 get us third equation here. This is the first state equation. The constitutive equation for inertia J is represented by next equation here. And the constitutive relation for damper B2 is represented by this simple equation. Substitute equation 5 and 6, we get the second state equation of the bottom here. D omega over dt, its proportions minus B2 over J times omega, and plus 1 over J times C. The vector matrix form for the state equations 3 and 4 is here, and 6, sorry. And the big expression with the state vector for R. It's a T times omega transform. And the output U, it's a from matrix from the omega. Now we consider the two cases of output. First case, the output equation is given by second, which can be written as omega 1 proportional omega capital minus T over B1. The associated matrices of the model are, as you may see, this expression here for A. Very simple, right? In this case, we notice direct feed forward of the input omega capital into the output omega 1 through the clutch B1. And case B, in this case, the output is simply the second state variable. Then we have the new matrices C and D here. The discrete time equation of the standard linear dynamic Kalman filter are represented here. The following assumptions are made in the derivation of these equations, as you can see here on the slide. First, the dynamic system is linear and time invariant, and the associated model matrices F, G, C, D are known. Second, all outputs Y are measurable. And third, the dynamic system is observable. Fourth, input disturbances or model error and output noise are additive, independent, and Gaussian white noise with known covariance matrices V and W. Typically, it is also assumed that D capital equals 0, matrix D. Modifying the Kalman field equation to include D is simple and straightforward. Kalman filter is an optimal estimator tool where the unknown variables, the state vector, are estimated by minimizing the error covariance of the estimate, given the measured data as time goes to infinity. Specifically, that at time step I, suppose that the actual state vector is x sub I, and its estimate value is x sub I hat. The associated estimation error, as you may see from these first equations here. A sub I is equal x sub I minus x hat sub I. As indicated earlier, Kalman filter follows a two-step process of prediction and correction. In the prediction step, a priori values of x sub I hat and p sub I of the state estimate and estimation error covariance respectively are determined. In the correction step, they use an actual output measurement y sub I. This is the a priori estimate are corrected to the posteriori estimation. The associated equations are given as follows. Predictor step, a priori estimation, as you may see from these first equations, and correction steps here in this equation. So prediction step, in a prediction step, it's all one step, one equation. And next three equations, it's a correction here. All three for correction. The initial values x naught, hat, and p naught of the estimated state vector and the error covariance matrix are needed to begin in Kalman filter recursion. These are chosen using prior information and intuition. In particular, we use P naught equal B. The initial estimate x naught hat is typically the initial value x from 0 of the state vector, which should be known. Observe the prediction and correction stages of this dynamic field. Compare with these figures for a static Kalman field, which has only the corrective stage. The matrix K sub I is called the Kalman gain. And you should note the similarity of the expression of the matrix to the scalar expression of the static Kalman field. Consider the diesel engine, in this example number sheet 6, diesel engine system, and suppose that the system parameters are as J equal O.5, K1, B2 O.2, and B2 O.25. As earlier, the input is omega capital, which is the diesel engine speed, and the state variables are T capital, which is the torque in the flexible shaft, and omega small, which is the pump speed. Take the pump speed at the system out. Then, the matrices defining the system are, as you may see, expressions for A, B, C, and D. Normally, it is more difficult to measure torque in a shaft than speed, particularly when the shaft is rotated. So in the present example, suppose that we wish to estimate the torque in the flexible shaft when the input speed is 2. The system is observable or constructible because it's non-singular, as you may see at the last expression here. And first, we use MATLAB to determine the eigenvalue of the system, as you may see at the upper corner. Very simple. It is seen that the system is stable because both eigenvalues are negative, and we can see minus. Also, the also the units of eigenvalue are frequency. And hence, we select the sampling period as T proportional for the O.2 to discretize the system. And next, we determine the discrete time system corresponding to the given continuous time system using MATLAB. The resulting state measurement matrix F here, and the input transition matrix G as follows. A zero order code has been used in the discretization. It is given that the input speed is 2. The measurement of the pump speed are simulated as its steady state value. It's approximately 4.9 plus random noise from a random number generator. The model for input disturbance and measurement covariance matrices are taken, as you may see, to expression for V and W on the bottom of this slide. We use the following MATLAB program to estimate the shaft torque and also the pump speed, using the measured pump speed with random noise. Estimated pump speed is taken as the correct value, unlike the measured value, which has noise. The error is the difference in the two quantities. In this slide, you can see the code continues. The results are shown in this figure. Note that in the presence of the significant error in both model and measurement, the Kalman filter has been effective in providing a reasonable estimate for the torque in the shaft. In particular, by comparing the measured speed and the estimated speed is slowly with x, with c estimated is the cross, and measured speed and the upper part. And it is clear that Kalman filter has virtually eliminated the measurement error. Let's see another point of our lecture: extended Kalman filter. Often, a linear model is just an approximation to a non-linear practical system. Also, the measured quantity may not be linearly related to the state variable. When the non-linearities are significant, a time-invariant linear model will no longer be valid. Then, the linear Kalman filter, which assumes a linear time-invariant model, cannot be used. The extended Kalman filter modifies the linear Kalman filter algorithm to take into account system non-linearity. The linear Kalman filter equations are modified given as follows in order to obtain the EKF. Predictor step, a priori estimation, as you may see on the second this equation. Corrector step, or a posteriori estimation, represented on the third equation here on the center of the slide. Next, we give an example for application of the EKF, extended Kalman filter. Here we have example number 7. And in this example, a passive shock absorber, that's moving right and left, unit has a piston cylinder mechanism as schematically shown in this figure. The cylinder is fixed and rigid and is filled with an incompressible hydraulic fluid on both sides of our piston. The piston mass is m small, as you can see on this picture. And its area is A. It has a small opening through the other side as the piston moves. This flow generates fluid resistance, which is nonlinear. Specifically, pressure drop is quadratically related to the volume flow rate through the opening. A spring of stiffness K resists the movement of the piston. Suppose that the input force applied to the shock absorber as F from T. Some important variables are defined as follows. V is the piston velocity. Q is the fluid volume flow rate through the piston opening. And P equals P2 from the right side minus P1 from the left side is the pressure difference between the two sides of the piston. Fk is a spring force. In a state space model of a system, we use the following variables: state vector x and input vector u. We will make the following assumption. First, there is no friction between the piston and the cylinder. Second, the areas of the two sides of the piston are equal, or approximately equal at value A. That is, neglect the area of the piston rod. And we can show that the state equation of the system looks like the second equation here, Fk dot proportions Kb. And see here from this first equation, its a matrix is a fluid resistance parameter. Note the non-linearity in the first state equation. Since speed is much easier to measure than the spring force, we will measure the only speed. And hence the output gain matrix is namely C here, 1 and 2. Suppose that when the system is discretized, we get the following nonlinear discrete time state space model, as you may see on the second equation for x1 and x2 here. And we have included the additive random model error term V1 and V2 in this equation. We will use the following parameters value A1, A2, A3, A5, B1, and B2 with their concrete value. In view of the model nonlinearity in this example, we will use the EKF, not the linear Kalman field. And furthermore, since the spring force is more difficult to measure than speed, we will estimate it through the measurement of the speed of the shock absorber. Suppose that the input force to the shock absorber is the sinusoidal function for u. It's simply u proportions to sine from 6t. For the purpose of the present example, the measurements of the absorber speed are simulated as values generated by nonlinear model. Are simulated values and of the system with added random noise, and the model input disturbance and measurement covariance matrices are taken as these two expressions for V and W. The discrete model may be expressed as second matrix here on linearization using the first term of the Taylor series expansion as a first derivative. And we get equation for F when I minus 1 here in this matrix. Also, you may see the matrix G here on the bottom. We use the following MATLAB program to estimate the spring force and also the shock absorber speed using the measured absorber speed with random noise. Estimated speed is taken as the correct value, while the measured speed, which has noise, is not accurate. The measurement error is the difference in the two quantities. At this slide, you can see continuing form. The results are shown in this figure. Note that in the presence of error in both model and measurement, the EKF has been effective in providing a reasonable estimate for the spring force. In particular, the comparing the measured speed represented by solid line curve, which have significant error in view of the added random noise, and the estimated speed curve indicated by symbol O. It is clear that the EKF has virtually eliminated the measurement error. I think that's enough, and I should tell you that is our final lecture. It was very pleasure to teaching you this course, and I think you will find your place, and this course will help you in your engineering career. Thanks, and see you later.